Welcome everybody to another DataWorks webinar. My name is Rebecca Medlin. I am a member of the research staff at the Institute for Defense Analyses and one of the 2020 workshop organizers. For those of you who are joining us for the first time today, DataWorks is a workshop that we've designed to build a community around rigorous statistical approaches to solving complex problems that we face in the DoD, NASA, and the national labs. The organizing of this event is a joint effort between IDA, DOT&E, NASA, and the American Statistical Association section on statistics in defense and national security. So just a few things to quickly note. For those of you who would like to view the materials, those are available on our DataWorks website. If you go to the webinar agenda and look at today's information, you'll find each speaker's materials there, so feel free to download. I'd like to thank our three speakers for volunteering their talks for our session today. So you'll hear talks on the topics of software, human factors, and autonomy. Our first speaker is Lance Fiondella. Lance is an associate professor of electrical and computer engineering at the University of Massachusetts, Dartmouth. He received his PhD in 2012 in computer science and engineering from the University of Connecticut. And his software and reliability and security research has been funded by organizations like DHS, NASA, Army Research Lab, the Naval Air Warfare Center, and the National Science Foundation, including a career award. So Lance, I will now turn things over to you.
Thank you, Rebecca. So the title is fairly self-explanatory. We're trying to modernize the software reliability research that has lagged modern practices like Agile and DevOps. And so this will be some presentation of our work in progress in collaboration with NASA. So this is work performed by my graduate and undergraduate students, as well as our collaborator from NASA Goddard, that's McKee. So, to motivate this, we know that the various organizations, whether it's NASA, DoD, or other government organizations, have various requirements with shall statements that talk about quality and related monitoring of processes performed by contractors and other performers, but there isn't specific guidance, and that's not how the government operates. So really what we're trying to do here is present some mathematical techniques that could be used on the data generated by those contractors to ensure quality early and regularly throughout the acquisition process. So this isn't a terribly appealing slide, but it communicates the kind of data we worked with. This is the metadata of a defect tracking system that NASA used on the project for the data we analyzed. And what's important to notice here is that obviously it's just the header of an Excel spreadsheet, but each row corresponds to a defect, and it's much more detailed life cycle, including 13 intermediate states from discovery to resolution. So some of the quantitative and temporal analysis and modeling is based on those subset of columns, but it also provides other rich data for essentially demonstrating that better modeling and prediction are possible to support oversight. So the talk is divided into three primary categories. The first one is a brief review of software reliability growth models, which are really only half of the puzzle. The second half talks about the resolution. So instead of just talking about discovery, which is really the focus of software reliability growth models, we talk about both discovery and resolution, the big picture of finding defects and then fixing them. And then the defect lifecycle modeling corresponds to the what goes on between the discovery and resolution. So as an overview, here's a chart of the defects in the project that were analyzed. You can see on each of these bars represents a version or build of the project. Some are major builds and others are minor builds. And you can see that there's also a decomposition by defect type or change request. The specific analysis on the following couple of slides is associated with the defects of build 4.0.0. And so this was a demonstration that software reliability growth models and the open source tools that we have created are applicable to software reliability defect tracking. Here you see a fit, or what we call the mean value function. That's that orange smooth curve fit to the defect discovery as a function of time. So on the x-axis, we have test time, and on the y-axis, we have cumulative failures. To note the predictions, everything past the dotted line is a prediction. So obviously, we want to see this curve tapering off as no new defects are found. Longer times with no failures are an indicator of reliability growth and software stability. Now, one thing to note also about this curve is that the first third, there's a kind of a ramp up phase. The middle sees the largest growth or increase, and then there's that tapering off. So when we look at the corresponding plot of the interfailure times, you see that the middle is the lowest simply because there's that increase in defects. And so we essentially have a kind of a reliability deterioration as we expose the defects, but towards the end, there is an improvement. And so the shape of that decreasing, or bathtub-shaped curve rather, is essentially relating back to the stages of the counting process on the previous plot. And then a third perspective on the data, as well as the model fit, obviously it's an approximate fit, is that the failure intensity, which one can regard as essentially the first derivative of that first plot, is the rate of, or essentially the instantaneous rate of occurrence of events according to the model fit. And you can see that the empirical intensity is essentially the reciprocal of the interfailure times. And we clearly want the failure intensity to be low, not high. And so some major defense acquisition programs, Air Force specifically, have used this specific plot to track KSAs, such as the failure intensity requirement of 1 failure per 1,000 hours. And hence you can see from this plot that obviously if we're only out to say 160 days, this plot provides a perspective on how one might project how long into the future it would require to achieve the contractually specified requirement, therefore providing insight into high-level risks such as schedule risk and the corresponding cost risks of overrunning the delivery target by months or potentially even years. And then, there's statistics built in where we can compute the time to achieve a desired reliability. So if we had a mission of 10 days and we want a probability of 0 failures equal to 90 or above, the model of best fit, that is that bottom one, the inflection S shape, tells us it might take us as much as 207 days or maybe about 9 months to achieve that requirement. Of course, these are just numbers for the sake of illustration, but such quantification, again, informs leadership if there is the corresponding schedule and economic risk. So all of that, and as well as our work on automating the interface, is summarized in this open source or open access journal article, and how to access the software, which is both free and open source in R. So that's there, but what we want to go on to now is, so that's the review of software reliability growth modeling in a nutshell. Let's move on to that more detailed defect tracking. So the defect database contained about 2,000 defects, of which there was some subset of 13 possible states from created to closed. So each row of the database corresponds to a defect and its life cycle, but it isn't necessarily the case that every defect occupies each state in this list of 13 possible states. So we'll visualize that. First the bad news and then the good news, of course. The original data was rather dirty, and as you can see here, the transition diagram is really uninformative. And so, we correlating common sense with what we were looking at, and then validating that with the engineers, we established that software engineers' primary focus, they have a hard job. It is to produce working software. And the last thing they want to worry about is some additional contractual requirement that requires they keep track of fixing the defects. Of course, we all know the value of that, but it's one additional distraction on top of the hard job they already do. So our goal in doing this work is to show that community, and this community, to essentially be a bearer of that message, that we can do better modeling with this data, and hence motivate the collection of quality data and interfaces that promote the collection of quality data. So help them see the value of these modeling activities for prediction and project tracking. There was also some questions about, were the individuals who were using the defect database receiving consistent training? That is, somebody might have assumed that a defect starts in state 0, whereas others thought it started in state 1, and other such inconsistencies. There was also evidence that there was batch activities, that is, multiple defects would be essentially closed out or transitioned from one state to the next simultaneously, suggesting that the contractor was doing this simply because it was in the requirements. But so the observation here is that a more detailed requirement that indicates not just the tracking of that it was done, but more precise data collection. And certainly there are opportunities to implement tools that automatically record this to ensure quality data. But again, making the software engineer's job easier so that this modeling can be done and motivate them with good predictions will be, what we attempt to do going forward. So here's the good news. After cleaning the data, we were able to reduce the life cycle to a much more meaningful Markov model, or simply state model, imposed with start and end states that are the arbitrary starting and ending states with the actual times in between. So one interesting observation here is that we did not construct one of those really simple Markov models with everything as exponentially distributed. We were able to actually compute the transition distributions on each of these edges, as well as the transition probabilities. That is, given that you're in the start state, what is the probability of transitioning to state 0 or state 1? So that is what's known as a semi-Markov process, and that allows us to do performance analysis on the time from the start state to the end state, as well as transitions between sequences. So one can regard this as a sort of pinball machine, and every defect might take a different path. The upper path corresponds to defects that ultimately get canceled in state 3. Maybe they're not repeatable, or they're really not defects, whereas the bottom path that begins at state 12 might go through some subset of the sequences of build integration. So one thing I would like to point out here is this is very promising. I really get excited about this because I think it indicates there is potential for not just doing defect tracking and resolution modeling, but this is what I believe to be indication that there can be better modeling of DevOps processes where there is continuous integration and continuous deployment. Of course, that might be even more data intensive, but I believe that this work essentially shows promise that similar things are possible within the realm of DevOps. So here's the high-level view of both the defects discovered as well as the defects resolved. So you can see there are two step functions. The one on the left is when they were discovered, and the one on the right is when they were resolved. So obviously, I would argue that the software engineer cares about what's going on in between, and they're not so concerned about statistical predictions as much as fixing those defects and making sure that the functionality is conforming to the requirements. So recognizing the competing focus of the software engineers and the reliability engineers who want to work in a synergistic fashion, this type of recognition of the difficulties of not just data quality, but modeling, and essentially being able to feed that back to the users so that we can improve the data quality. So the next step is to talk about how did we get that defect resolution curve. And so the very simple approach was to take the entire data set of times between discovery and resolution and construct a PDF from 19 different distributions, and MATLAB, a generalized extreme value, fit best. And if we take the expectation of that PDF, we simply shift the discovery turn curve right by the mean of that distribution, which might have been about 60 days or so. Clearly, just going back to the previous slide quickly, one can observe that the defect discovery curve can also predict how many defects we will discover in total, whereas the defect resolution curve will tell us when are we going to fix these things and how much of a time lag might there be. So this is obviously something leadership cares about because they want to know when the problems will be solved. And so the simplest answer, if this model is a good fit and there isn't a severe heavy tail, is that on average, we might expect with some, and we could even do statistical inference on this distribution, is that once we've exposed all the defects, we'll require about this much, the mean time of the distribution of best fit to also resolve those so that we can proceed to the next stage of integration. And so this slide is just intended to recall the more detailed defect life cycle in all those states. So in other words, we did a similar analysis on every single edge within the semi-Markov process so that we could do some analysis, derive what's called the fundamental matrix, and essentially predict the mean time between the start and end states, and to do that analysis as an alternative to the simple time between start and end. But more importantly, instead of just doing good old-fashioned statistics with maximum likelihood estimation, and to make this a practical process that can be used throughout the defect discovery and resolution process, we can use the data available to us at that time. So what we have used here is a simple technique called censoring, where, and this also finds applications in medical studies, for example, survival, or people who try to quit smoking and maybe drop out of a study. So here we divide the statistics on defects into the left-hand product series, which is the set of defects that have been discovered and resolved. So essentially we have the product of the probabilities of the times between discovery and repair. And the right-hand product series corresponds to the remaining n-k defects that at time big T have not yet been resolved. So we can use, instead of discarding that data and biasing our estimate, we can use the partially observed data of having found defects but not yet resolved them as part of our maximum likelihood estimation process. And so we apply this at every single time a defect is discovered or repaired, and we're able to produce essentially an online procedure that is not retroactive and can track this is just the resolution curve as it occurs. So here we're comparing the very simple, what we refer to as the distributional approach, which was just that PDF shifted by the right, and a similar calculation on the semi-Markov process to determine the mean time between discovery and resolution. And what we found was that the estimations, or the ability to track in terms of, say, sum of squares error as it occurs, or a one-step ahead predictive mean square error in terms of some time delta, say maybe some weeks into the future, was slightly better than the distributional approach, but that the computational complexity of the Markovian approach wasn't necessarily justified because the distributional approach performed well, at least in the context of this data set. And we can also analyze the resolution intensity. Of course, this is a gross approximation. We see that the smooth curve is by no means does not track the empirical data well. And so my note here is that what would be very interesting from a data analysis standpoint would be to get one's hands on what was the software team doing, what activities were they doing, and how long were they working on these various defects to resolve them. So if we had multiple covariates associated with activities that correlate strongly with defect repair, we could essentially apply a more advanced covariate software reliability model to better estimate how much effort is required to resolve the defects. And with that, I will conclude and thank the sponsors, both NASA, and some of the support came from NSF. So thank you, and I'm open to questions at this time.
Thanks, Lance. Yeah, we'll take a few minutes to see if anybody has questions they'd like to ask. So show both cumulative defects discovered and cumulative test time. Are you assuming one discovery per failure?
So to clarify, the counting process corresponds to unique defects. If a failure occurs the same root cause occurs 6,000 times, we only counted once. But of course, there is typically some retroactive data cleaning that identifies those unique root causes. And it is a Herculean task. Obviously, that requires expertise. And we're, at least to my knowledge, we're not at the point where we can do automated defect analysis for that kind of classification. So to answer your question, those are unique defects discovered as a function of time that may deviate from the requirements.
I'm not sure if you see that follow.
Yeah, I see it. So, yeah, sure, that's a popular, I understand I read into that question as to, could we not apply models like CROAMSA, for example, which are commonly required in the contracting community? And I guess my honest answer is I'll have to think about it. I think it could be possible, but the fix effectiveness factor requires perhaps more fine-grained tracking because we show a state model transition from discovery to resolution, whereas the fix effectiveness factor might require a second attempt. And hence, it's possible that the quality of the data or the detail of the data provided that we did this analysis with would not be sufficient for that kind of fix effectiveness factor calculation that you're asking. There is the possibility that defects are discovered by other processes in code reviews, and hence, again, I'll harp on these covariate models where it's not just test time or wall clock time, but actually multiple activities. So the covariate models, for which we hope to publish an open source tool for soon, and I'll certainly try to share that with the community, would document the number of hours conducting multiple activities. So for example, we might have the number of hours the team spent doing code reviews, another column, the number of hours the team spent doing other, testing activities that are actually executing the code as opposed to just reading through the code. And one other generalization to note is that this multivariate, what the testers are doing, isn't just applicable to reliability data where there are defects that are deviations from the functional requirements. There is certainly the potential to apply this in the context of security testing. So each one of those columns or covariates could apply to a specific vendor's tool to expose vulnerabilities as well.
All right, thanks again, Lance. And I think now we'll switch it over to our next speaker. I'll give a short introduction. Charles is our second speaker, and Charles provides test and evaluation, system engineering, human factors engineering, strategic planning, capture planning, and proposal development support to companies supporting the Department of Defense and the Department of Homeland Security. Most recently, he's worked on efforts to support the evaluation of transportation security equipment, systems deployed to airports and intermodal facilities. Charles has led the design and development of a common graphical user interface for new checkpoint computed tomography systems, something that I think he's going to tell us a little bit more about today. Another thing to note is that Charles remains very active in the T&E community, recently serving as president of the board of directors for the International Test and Evaluation Association. So Charles, I will turn it over to you. And it looks like you got the screen up.
You can see it?
Yep, we can see it and we can hear you.
Okay, great. Oh, good, wonderful. All right, so hopefully nobody will yell bingo. But we'll go ahead and get started. So I'm going to have a co-presenter, Dr. Simone Urchoff McKnight is going to help me with this. So Simone was my lead analyst on this program, and so she's going to help me out when we get to some of the hardcore data. So what we did was we did a program for the Transportation Security Administration, TSA, and if you've ever gone through a TSA checkpoint for your baggage screening, that's your carry-on property. TSA is deploying new technology called computed tomography, CT. That's a 3D-dimensional X-ray system that the medical community uses and gives you a 3-dimensional image of the bag and everything in it. It also has algorithms to detect explosives. And so Congress directed TSA to deploy, well, procure and deploy these systems, and they hired us to help them develop the graphical user interface for the system. And so that's what we're going to discuss today, is our process for doing that. And it was really a test, build, test, build, test, build, and lots of use of quantitative as well as qualitative data. All right, so let's go to the next slide. Can I do that? And it's not letting me. Okay, let's go there. All right, so there's myself and Simone. By the way, you did a great job introducing me. And then Simone, like I said, graduate of George Mason University, and has been working at TSA for the last 2 years, 3 years? 3 years. All right. Okay. Purpose and goal. Inclusion of human factors. So they brought this to us. We support the human factors or human performance branch of TSA. And really, HPV tries to apply human factors principles to everything that's being done at both the checkpoints and checked baggage within, and everything at a checkpoint, just to make the human experience better, both for the TSOs as well as the passengers. And so the goal of this project was to really improve and make sure and optimize the graphical user interface on these very complex systems. And, okay, let's see. All right, so here is a little disclaimer, and also just to give you a picture. So for those of you who've never seen a CT image, what you see here is a sample. And what we did was we actually built bags, and we put prohibited items. You'll hear me as Simone and I talk about PI, prohibited items. And so you see a couple of knives in here. For if you're not pre-check, you can't have your laptops. That's why you have to take them out. You got to take your water bottles out. So those kinds of things. And so I wanted to show you this example of a three-dimensional image, so you could see what they're looking at. Okay, and we'll get into some of the aspects, but you see there's different colors. You can see the layers of the bag. You can see the how things are sandwiched in between things, and how difficult it might be for somebody to clear a bag. And when you figure that you've got 300 people all waiting in line who are waiting for their plane, the TSOs are under tremendous pressure. Okay. Let's go to the next. So we'll get into it. All right. So what is human factors? So human factors is really was developed 70 years ago, an output of World War II and people flying airplanes, and trying to make it so that people didn't fly their airplane into the dirt, and make sure that they knew where their flaps were and things like that. So it's all about marrying cognitive human, how the brain works with machines, and making those systems, the human computer, human system, your car, whatever you want to call it, interact. And why do, if you've ever tried to follow GPS, and the great commercials that are out there where it says go left and you go right, and you drive into a Starbucks because you're following the GPS. That's human factors. Okay, let's go to the next. So what do we do at TSA? And I talked about this a little earlier. Our goal was to design a common graphical user interface for the CTs. The purpose was more effective and efficient screening, ease of switching, training efficiencies, and system architecture flexibility. Okay. Just talked about that. On the right here, you'll see our process. And this kind of is an overview of the tasks that we had in our project to review, look at the research, look at what's out there, look at the systems, identify the key elements, do our prototype development, run our test, and then revise and repeat. Test, fix, test, fix, test, fix, and then provide the result of our project was a design guide, which will end up as for those of you who've done acquisition in the federal government, in order to put out an RFP, you have to develop what's called a functional requirements document or a system spec. And so that was our end product. Okay, step one, review. What did we do? So this was a 2-year project and this is kind of an overview of the project. You'll see task 1 was research, task 2 was data collection, and then we did requirements development, iterated user testing, collect and analyze the data, and it was spread throughout. You can see some of the testing that we did and when we did it. Part of some of our challenge was when we started the project in September of 2017, there were 4 CT vendors and only 2 of them were actually in airports. And they didn't get the other airports, they didn't get them into the airports until January. And then the other 2 systems didn't go into the airports until April and May. It kind of made things a little difficult for us to really understand the systems under development and how different they were and how the TSOs would interact. So we developed a whole process of using the systems in the field, the systems in, so TSA has TSA has the TSIF, the TSA Systems Integration Facility, which is at Reagan National Airport. And then DHS has a developmental test facility up in Atlantic City called the TSL. And that's part of DHS S&T. And so the systems were all there. And so we were able to actually look at these systems in a laboratory environment. We brought TSOs in to actually operate the systems, run bags through them, and then we would conduct focus groups with the TSOs on what they liked and disliked and things like that. I'm going to get into a little bit of the data there. And then later we went into, once we developed our prototype, so you can see the iteration 0 was our first prototype. And then we did our iteration testing. We did multiple tests across multiple airports. And then we did our final results. Okay, step 1 was look at the systems. I'm going to go to the next slide, slide 14. This was my favorite slide of the whole thing. What you see on the right are the 4 different vendor interfaces that the vendors developed. And I call it the Wild Wild West. You've got one with 2 panels, 2 with 2 panels, one with another had 3 panels, another had 4 panels. The bags would, you can't really see it because we had to blur the images, but this is the same bag on 4 different, scanned on 4 different systems, and they look completely different. They have different colors. They have different orientations. One system, the bag, the wheels are on the left. Another system, the wheels are on the right. Another system, the wheels are on the bottom. It's vertically oriented. So from a human factors point of view and from a TSA, an operator point of view, they don't know what they're getting. They all had different tools. You can see some of the tools on the bottom and on the side, all these buttons. Imagine what it's like if you're a TSO, Transportation Security Officer, who's trying to operate these machines, and you change airports from Reagan to Dulles or BWI to Philly. And that happens all the time, and you go from one vendor to another vendor. TSA looked at this and went, oh my God, we've got a disaster on our hands. And so the first thing we did was we looked at these systems and we baselined the systems of what functions did they provide and what tools, how did they project the images, what colors did they use and why did they use them and how did they use them, and was there a standard by which they used these? And then we asked the TSOs, well, what's good? What are you using and why do you use it, and what's important, what's most important to you to screen these bags? And that's where we get into the next step. So first question we asked was, well, what tools are you using? And so we did a frequency analysis in the lab with TSOs running the systems in the lab, and we watched them and we went through the video and we recorded all the tools that they used. And of course, number one was rotate the bag. And then you can kind of go through and see the percentages that go along with it. This is vendor number 2. And then you look at the next slide, it shows vendor number 3. And so you can really get an idea that between these 2 vendors that we had available at the time, the most important things were rotate, pan, and zoom. You see it in this one. You see slab, you see annotation. Clear bag and search bag you have to do for every bag. That's the TSO saying this bag is clear, move it on. Search means that's when it gets diverted, and they're going to then take you to secondary, and they're going to open up your bag and find the water bottle in it and go, you know, you can't have a water bottle on, you can't bring this through. Hopefully it's not that you have something else like a gun. So rotate, pan, and zoom were important. And then we got into the other tools. And so you also see there's different numbers here. There's x-axis, y-axis, z-axis, slab. You've got color metric, inverse, opacity slider, isolation, things like that. So they had all these different tools, but they're really not using them. So, you know, it really got into, then you start getting into, well, why do you have this and do I really need it and why? The other thing that we did was there is a standard usability scale called the SUS, the System Usability Score. And this is a commercial, typically used in commercial for usability. And you answer, you have the operators use it, and you operate the system, and it comes back and it asks you 10 questions on a sliding scale, and you come back and it then calculates a score based on this this distribution. Google, everybody's used Google, is 100%. That's your most simple. It's very, very easy. And so what you see here is that these vendors were all over the map. In fact, you can see with vendor number 1, they had a score that was very different at one airport than from another airport. Vendor number 2 was pretty consistent, and vendors number 3 and 4 didn't get very good scores at all. Go to the next slide, and you can kind of see we also asked them questions. We did ask them some comprehension questions about the icons. What was important here was what we found was that the vendors who had a lot of tools, a lot of icons, their comprehension scores were much lower. Whereas the vendors who had the least number of icons, the comprehension was much better. And it all got down into orientation and usability and what the operators liked and disliked. Okay, so then the next step was prototype development. And so what we did was, I call this, we built our Frankenstein's monster. We built the Franken-GUI. We took the head off of one, the legs off another, the arms off another, and the torso off of another, and we pieced it all together, and this is what you got. So Simone's laughing at me. But we took the things that were most important, rotate, pan, and zoom. We did a whole study with emulators. was 2 panels better than 3 panels, better than 4 panels, and they told us 2 panels was better. We asked, you saw the frequency study, what were the tools that they used? They used TriMat number 1. That's where it shows all 3 colors. And the 3 colors are organic, inorganic, and metal. And then there were some others called inverse and what's the other one? Negative. And those were least used, but what was funny was you actually had some TSOs who just swore by it, that I've got to have inverse and negative. And so we kept them in there. So we gave them all the tools that they needed. We gave, annotation is a big one. So when you do find a threat or a prohibited item in the bag, they have to mark it on the image and send it to secondary, and then the image comes up, and the TSO at secondary can then see, okay, I see this object in the bag. That's very clearly a gun. They want to know where it is, or if it's a knife, where it is, and they got to know where it is in the bag so they can go find it, and they don't want to cut themselves or hurt themselves. And then the tools on the right of our image were our, the right panel we decided would be our threat isolation panel. So the left image is your regular, the bag image, and on the right, if there's an automated alarm, like an explosive in the bag, it will show up in here automatically in the right. If there's a laptop in the bag, so one of the vendors actually developed an algorithm that if there was a large electronic or laptop or iPad in the bag, it would isolate that image and isolate it into the right panel. So you could then rotate, pan, and zoom the laptop. You could see if anybody had tampered with that laptop, if anybody had stuck something in that laptop, hidden the knife in between the pieces of the laptop or in the battery compartment or something like that. And then another vendor, and we don't have a picture of it here, another one of the tools, one vendor had something what they called surface rendering. And that was kind of a, I don't know that we have a picture of it, but that was basically, they gave, it showed the objects in the bag, but they kind of cartoonized them so that you could see the surfaces of those objects. And this was developed in the medical community so that when they ran a CT, they could see the heart and the lung, and they could see the blood vessels on the heart, and they could see the aorta coming out of it, and they could see the aneurysm growing on the aorta, and things like that. And so with CT, with TSA, imagine opening, you can actually open the bag and look at it and rotate through the bag and zoom into the bag and see, oh, that's an apple. That object, that organic mass isn't an explosive. It's an apple. It looks like an apple. It's a peach. It looks like a peach. And you could see the grapes. You could see, you know, the moms who are bringing their kids food on the airplane, and you could see the carrots and the grapes and stuff. They look really weird when it's an X-ray image. But when you use surface rendering, it just brings it right there to the TSO, and they can go, oh, I know exactly what that is. I don't need to worry about it. And then the last thing on here was threat tray. So every automated alarm appears in the threat tray. Everything you annotate appears in the threat tray. And the number one goal that we were trying to prevent was clearing a bag that had an alarm in it inadvertently. That would be a bad thing to do, is sending a bag to the clear line and having a passenger pick up their bag and run off to the airplane when, oh crap, I didn't mean to do that, and they accidentally hit clear. And so our process, our workflow was designed so that they could not do that. So they have to clear every alarm in the bag, every automated alarm. If they create an annotation, they have to clear it. Otherwise, clear bag is never activated. They can only search that bag if there's an alarm still in the threat tray. Once all the alarms are cleared, clear bag gets activated, and they can hit clear bag. But otherwise, can't do it. So that was our number one workflow issue. Okay, let's see. Methods. So I talked a little bit about this already. We did surveys, we did focus groups, we observed the systems that did checkpoints, and then we did both qualitative and quantitative analysis of our prototype. And the prototype actually had built-in subroutines that would collect every button that every TSO pressed. It would collect time data on the whole thing. And so we had some great data with which to conduct our experiments. And go to the next, testing considerations. Of course, we had to deal with getting TSOs who were trained in CT versus those who weren't. We had to go to airports that had the CT prototypes that were there. We couldn't just go to an airport that didn't. If the TSOs had never seen a three-dimensional image, that would be unfair. And then we had to, of course, design our experiments to make sure that we had a balanced test and that we would have statistical confidence in the data that we were looking at. And I'll let Simone get into some of that. And the next slide you can actually see is a picture from one of our tests. We had our prototypes set up. We had them on 27-inch touchscreen monitors. We actually, later Simone will talk about, we did a test of touchscreen versus mouse. We ran them through a training session, and then we gave them 300 bags to go through and test. And then at the end, we gave them the SUS, and we did some alternative surveys and got their feedback on different ideas that we had for the threat tray. We had multiple threat tray options. We had multiple ways of doing annotation. And annotation in the 3D environment, I'm gonna let Simone, I'm not gonna steal her thunder on that one, but that was one of our largest challenges, was how do you annotate an object in 3D space? And I'm gonna turn it over to Simone now.
Okay, awesome, thank you, Chad. So at this point, essentially, we generally planned to try and go through each of the different components that we have for both the quantitative and qualitative data analysis. Obviously, our results and any of the limitations we discovered identified certain logistic constraints. So we had to use parametric versus non-parametric procedures, and we just essentially accounted for, the exploratory process of data analysis as we went along through each iteration, as well as trying to build in through each iteration things that we learned from the previous one that we had to account for at the next airport. So overall, we had logistic constraints that did limit some of the quantitative data that we had, mostly from the initial prototype test. And then our qualitative data typically provided general system feedback. We had some frequency analysis and sentiment analysis that we could run to try and inform why we found some of the results that we did within the quantitative data. But at the same time, we're working to some degree with limited inference, and we did took the best of our ability, tried to put all the pieces together to form the clearest picture for TSA on how to proceed with the development of a single user interface for these systems. Right, so this is a general overview of what the first iteration looked like, and this is what we called iteration 0. We pretty much had on the left, we had one of the image panels of the bag, and then on the right, we had another image panel. And if you had anything that you particularly wanted to focus on in the bag, that would show up in the right image panel. On the left-hand side, underneath the first image panel, all those tools manipulated the first image panel, and then the same on the right, all the tools underneath that image panel manipulated that particular image panel, so that things essentially were congruent with each other. On the right-hand side, we had the threat tray, so if there were any system threats identified by the algorithms, TSOs would have those things pop up. As they went through them one by one, they would highlight so that they knew which one they were working with, and then they were categorized by color. So Depending upon what type of threat the system identified it was, they were going to be different colors. And then the pink ones were the operator identified threats. So say that the system wasn't really programmed to identify a certain type of item, like a water bottle or something, according to its algorithms. If that's not something that's supposed to be in a bag, a TSO could identify it, they could click on it, annotate it, and it would come up as an operator threat. Whoops, sorry about that. So for the first results of the iteration 0, we went to one airport and tested this. We found that while it was okay and comparable to some of the vendors, it wasn't the best according to the system usability scale. So it got a percentile rank around the 50th percentile, and that essentially gave it an okay rating. And what we were trying to figure out is why exactly this happened. So we looked at a lot of the qualitative data and the sentiment analysis for this particular set of feedback. We did have a relatively small sample size. It was only 16 people, but at the same time, that was a pretty good recruitment process because we had to pull active people at the airports, and it's not common to be able to pull that many people at one time because they have to pull people off of shifts who actually have to scan passengers at the same time. So what we did find is that there were several additional improvements to the design that we had, the initial design, as well as the rationale for the performance trends. And we found this through the alternative surveys and the frequency analysis. So one example is essentially how did we annotate some of the images that we had for whether or not were axes supposed to be labeled, should we put measurements for objects that they're trying to identify, whether or not they should actually flag them. And so the TSOs gave us ranked data, and we figured out what was the best way to present some of the information that they wanted to see. We also found that they preferred what type size monitor, so a 27-inch monitor was ideal for them. TSOs did believe that the use of CT was actually a good thing because that 2D X-ray was going to become antiquated over time, and it actually might speed up the passenger process. They also liked some of the newer features that we included, which were features that allowed them to cut through the bag and look at things more closely, look at texture in the bag, so that was similar to surface rendering that Chaz was talking about, and looking at threat and laptop isolation. So previously, you always had to take your laptops out of the bag, and at pre-check now, you don't necessarily have to, but if you have multiple, you should. This might allow for them to not have to have any passengers take their laptops out of the bag if they can isolate the image on its own through the algorithms in the system. So they also wanted to be able to improve annotation and adjust the size of the box around different objects a little bit more easily. It was pretty cumbersome first effort at how to annotate different items within bags. So that was part of the reason that they had pretty low scores for everything. And then these were the results of the sentiment analysis. So we had kind of negative versus positive trends. Obviously, the 100% negative is when they encountered errors in the system. Not to be surprising. But they really found a lot of positivity in the features that were relatively easy to manipulate, that were really a lot of the common ones that they used. And a lot of the ones that they essentially said we didn't like, we figured out from one-on-one interviews exactly what it was about those features that they wanted. So for the image panels, the negative aspects of it is they said they wanted larger image panels. They wanted to be able to see the bags more clearly, and it should take up the majority of the screen. So these were things that we factored into the next iteration. So we went through 3 iterations total, and essentially all we did is we took all the information that we had from the first iteration, and that was the review process. We developed the Franken GUI, as Chaz calls it. And then now from the first iteration, iteration 0, we took all that information and went into the next test in order to figure out what are some of the best ways to update the system and hopefully improve the system usability score. So we essentially performed a parallel experimental design in the next iteration. We updated some of the system functions, the ones that were causing errors, obviously, so that they didn't encounter them again. And we updated the surveys because we obviously introduced new tools or altered some of the tools in order to answer new questions or questions that we realized we weren't able to ask in the first iteration. So over the course of the next iterations, we ended up testing at 6 different airports. So for the first iteration, we only tested at 1. For the next iteration, we called it 1 to 2 because there were some tweaks in between some of the tests. We tested at 4 different airports so that we could really get a swath of people that had used all the different types of vendors, because we did account for the fact that depending upon which vendor you were using, when you saw how different they were in that first slide, it was quite likely that your experience with a previous CT system may influence your experience with a new interface. So we wanted to be able to account for that. And then we had the last iteration that we tested at one airport and delivered as our final product. So essentially it was iterative testing as typical with human factor structure. So it was repeat and refine over multiple iterations. So the second iteration was pretty much the same, but we had a 2x2 design where we really focused on what type of threat tray they should use and what type of annotation was going to be best for them, because these are the two most common tools that TSOs use. And one of them was the EDS threat tray, which is actually an existing threat tray that they already used on a different system at the airport, and then a new one that we designed. And then there were two different annotation styles, and both of them were drawn from two different styles that the vendor systems that already existed offered. So what we found for this was that there were really no significant differences in threat discrimination for either of the conditions. So performance-wise, we weren't really going to suffer from which type of threat tray we had. So we cared both about performance as well as whether they even liked the threat trays or not. We did determine that the EDS threat tray offered the greatest opportunity to increase image channel real estate because it was just a little bit more compact in its structure. And looking at performance statistics, both D prime and A prime, we found that following the threat tray and annotation combinations, we wanted to use EDS and what was called the drill down method for annotation. So specifically for annotation, we found there were no differences in threat discrimination. So the drill down annotation method had the greatest opportunity to become the fastest method, which is what they wanted. If they had to manipulate something, they wanted to do it as quickly as possible because they have a time pressure to get passengers through the airport. So the two different methods and why drill down was faster is that drill down was where they would use an algorithm in the system that they clicked on an object that they wanted to annotate. They wanted the system to identify, and it would essentially place a box around the object that they clicked on. Box draw is where they essentially tried to draw a 2D box around the object, and then the system would place a 3D box around where they drew. So what we found with these results is that the system usability scale score increased quite a bit from iteration 0 to iteration 1. We jumped from the 50th percentile up to in the 82nd percentile, or in terms of 50th sus score to the 82nd sus score, and the percentiles went 50th to 90th. So we moved from a D grade, which was okay in terms of an adjective description, to a B grade, which is technically considered good, kind of on the cusp of like you're doing pretty well in terms of the system usability scale scores. So already we're seeing that iteration 1 to 2 is performing equivalent, if not better, than almost all of the other vendor systems that we tested in the review period at other airports, as well as our first iteration. And a lot of that was due to the fact that we cared about what the TSOs had to say. So the combination of survey and experimental data suggested the TSOs desired and used different, but they used different features. So what they said they would use a lot, they often didn't. But they did want to use individual density sliders so that they can manipulate the different types of densities of organic and inorganic on their own and not together within TriMat. They wanted to be able to see all the identified threats at once as well as one at a time. And they pretty much spent 80% of their time rotating an image and 95% of their time using the standard bag view. So we had a little bit of conflicting evidence, but due to the fact that they wanted individual sliders, we did end up incorporating that into our next test and to see whether or not, because they wanted it, would they actually use it if they was made available to them. We also tried to figure out how much time annotation took for them, which was approximately 13 seconds. And where they spent most of their time, which was adjusting and rotating the annotation to try and get it perfect. So what we wanted to do is try and improve annotation within the 3D space, which is going to be relatively complex, in order to increase the speed at which they could do their job, make passengers happier, and make their lives less stressful. So the last iteration test, which developed our final product, was another 2x2 design, but so we worked with the threat tray. We chose the EDS threat tray for this test. Annotation, we looked at new kind of hybrid element of the annotation design, and then we tested system modality because we had the opportunity to use touchscreen methods, and there was the idea that maybe TSOs might shift to using touchscreen in the future. Some other systems at the airports are already using touchscreen, so we wanted to see whether this was a feasible interface to go back and forth between using a mouse and using a touchscreen interface. So we did mouse by touchscreen, and then we had the EDS threat tray, and then we had a hybrid version of annotation that was aimed to be faster in terms of placing a box more clearly and essentially creating nodes that were clear for where they were moving the box versus adjusting the edges so that they could adjust the annotation much more quickly and easily. And considering the fact that several of these people were relatively new to using the systems, as Chaz had said, there weren't many systems currently available in the airports, or they had only been using them, they had only either completed their certification training or had only been using them for a few months, we needed to count for training on the system as well. So what we found that with system learning, the timing and accuracy of using the system actually increased significantly within 1 hour of training. So that was actually a vote of confidence across all the tests that TSOs were getting used to the system relatively quickly, and we didn't necessarily have to account for any concerns with learning. The system modality as well, we saw differences in timing and accuracy. So the accuracy for touchscreen versus mouse was relatively equivalent, which was great. We didn't have to worry about anything. But with the timing, we did find that the touchscreen was much faster than using the mouse, mostly because they had more direct control, especially when using annotation. It was much easier for them to use the touchscreen and manipulate the bag directly. And the last one was the iteration, looking at timing versus accuracy. We saw that with timing, iteration 1 and 2 was a lot slower than 3, but the accuracy was about equivalent. So we were seeing that with each of the upgrades that we made from each iteration to the next, we were actually improving the system, but we weren't harming it in terms of accuracy. And that's something that TSA cares about. And as passengers who travel, we should care about that too. So this graph shows the accurate adjudications with no automatically detected threats on laptops. So these are the bags that are most likely to be processed quickly, but also most commonly to be encountered by TSOs. And this was solely after 15 minutes of training, but we did track this data over the course of an hour in terms of their first run through bags with the experiment. On average, it took about just under 30 seconds to review each bag. And each additional automated threat, we also found that it increased the time by 5 seconds, and laptops increased at about 3.5 seconds. So we actually were able to kind of drill down to a pretty granular level and find out what is actually impacting their ability to process bags quickly. And so what we found as well with comparing modalities and mouse versus touchscreen is that there weren't any significant differences in threat discrimination between the mouse and touchscreen. And this is both calculating D prime and A prime. There were no significant differences. Just to account for some of the oddness in the data in terms of we ran the non-parametric A prime as well. TSOs in the touchscreen mode were significantly faster though than in the mouse mode. So touchscreen in this case would be considered a viable, but not necessarily necessary alternative to using the mouse. The mouse is a standard platform, but a lot of TSOs were excited about shifting to touchscreen, although many had concerns. Potentially the gorilla arm effect, where if you raise your arm too often, it's going to actually cause problems in your shoulder, and as well the potential that the screens could get messy or that they'd have to use gloves and whether they'd be compatible with that. So for annotation, this is one of our, this was a bear for us to a great degree, because trying to alter how to create a box and adjust it within 3D space and to do it relatively quickly was quite complicated. First, they had to be able to rotate the bags and adjust the edges by rotating the bags. And this was built within an emulator as well. So we had to create a relatively simple process within the emulator, but also make it accurate and quick enough that TSOs could adjust it relatively quickly, both in a mouse and a touchscreen fashion. So iteration 3 actually took longer per bag to adjust than iteration 1 and 2, but it took longer to complete than at any of the other airports in 1 and 2. So we had 4 airports in 1 and 2 versus 1 in iteration 3. While that doesn't make for a great story, especially since we don't know why it took longer, we do know that we got better with each iteration, and TSOs liked the annotation hybrid method in iteration 3 much better than they did in iterations 1 and 2. The hybrid method was near perfect, and the system would draw a box based on a single click, and by increasing both the minimum size of the box as well as the touch points, it made it much easier for TSOs to adjust. They were much less frustrated on the whole at the end of the day. So the first graph does show all the data, and it's one data point per participant. The red circle is the mean and the bar is the median. And this includes the box plot overall. So the data for the people, this data essentially shows you everything you might want in terms of getting at the granular level of how the spread of participants, essentially where they were clustered, as well as the differences between mean and median. We do see that the hybrid method was the fastest, and we did have to transform this into z-scores merely for the fact that we needed to just scrub some of the data for public consumption. So on the discussion of annotation, I'd like to make a quick aside, very similar to the point I was kind of alluding to, is that developing 3D annotation is a really difficult process. There were significant changes to each iteration of annotation. And in iterative design, you don't typically make massive changes from one iteration to the next like we did in this process. But since we had essentially a shortened time frame that we had to operate on, we really used as much of the qualitative and quantitative data that we had available to inform the necessary changes and interpret performance issues. Because the qualitative alone and the quantitative data alone did not give us enough information in order to move forward and figure out what was actually causing the problem for them. So we investigated the time to make annotation, considering the time and actions between when TSOs clicked the annotate button until they confirmed or canceled the annotation. So we didn't necessarily know exactly what was going on in between, and that's where the qualitative data came in and informed what was happening and why they were taking so long, or why they were so quick or frustrated. And so overall, what we found was that the drill down method of annotation performed well, and there was no difference in time to annotate by input type, time to annotate by their actions, or adjust the annotation. But the TSOs were having a really hard time just clicking on the buttons to adjust the box because it wasn't placed as well as they wanted it to be very often. So that just led us to, okay, we have to differentiate the touch buttons, touch points a little bit better, and we have to make them larger, alter them by color, and improve the box size so that it's easier for them to access quickly and adjust quickly. And so we looked at different levels in detail, examining how the users prefer and use different tools and elements of the interface. And those provided insight for the best ways to alter the design, not only from their qualitative data, what they reported, but we just looked at differences in input types. So mouse versus touch screen, did they have differences in how they performed? Did they have differences in whether or not they were touching the center button touch point, or they were trying to alter the sides of the box? So ultimately, what we ended up developing was a 3D box that was automatically placed where the TSOs click on the screen so that they didn't have to take time to draw. And we aimed at focusing on improving the algorithms to enhancing the placement in the future that would require less adjustment. And these types of algorithms are constantly updated and improved upon. So it's something that TSA could easily create so that in the future, TSOs might actually not have to adjust the annotations at all. We identified that touch point base was the best for them. So touch points had a minimum size for easy selection to manipulate, and they need to be able to adjust the edges and move the box in very unique and different ways just for the ease of use. So we created a colored center touch point, and we created large exterior touch points that were easier for them to touch, both within mouse and touchscreen modalities. And so lastly, the combination of survey and experimental data suggested that TSOs regularly overestimated the frequency of use of several different features that they specifically requested. So individual density sliders, negative grayscale, and slab or slice, like Chaz was talking about, they demanded this from the start because these were the common tools that they used on their former systems. They pretty much used them less than 5% of the time. So while they liked seeing all the threats at the same time, they wanted the option to turn off that feature as well, and that actually proved useful. But when it came to the mismatch between their desire for certain features and whether or not they use them, what we found is that there are some tools that are worthwhile to grandfather in and potentially phase out over time because they're used to them, and an abrupt change from one system to the next might be tough. They have all these tools on the X-ray imaging systems, and they just feel a comfort in having them available on the CT systems. So initial transition might suggest that we want to keep some of these tools, but then start to phase them out over time because the TSOs are going to identify that they're not necessarily useful for them over the course of time. So ultimately what we found is that iterative testing is incredibly helpful and develops a relatively decent product for TSA to work through and push forward so that they don't have 4 different vendor systems potentially all at the same airport and creating difficulty for TSOs to train on and transition between. So we went from essentially something that was a D grade and just okay, compared worse than some of the current systems out there, to a B grade in the 93rd percentile that was performing just as, if not better than, all the other systems out there. So we did also develop a more detailed understanding about TSO preferences for common GUI options that were identified. For example, using a ruler on annotation was a key element that they desired because it helps them abide by their standard operating procedures much easier, because certain things they need to either investigate or not investigate depending upon how long a knife is, for example. And some elements of TSO preference, again, may be due to familiarity with current tools that are not going to be useful on newer systems. So we needed to create considerations for how to transition users to newer systems and phase in and out of certain features. So lastly, the qualitative data, while a lot of people think it's not as important as quantitative data, the open-ended feedback provided us a lot of valuable information and informed why we saw some of the quantitative trends that we did. So it's something that is always important to incorporate into the testing lifecycle. And we gathered the following inferences, like I said, that they pretty much didn't match their expectations with their performance standards. So there are certain features that we were able to combine and not have to worry about in the future. And there are some features that we were going to maintain and then potentially suggest to TSA that they phase out over time. So ultimately, the common GUI in iteration 3, we found that there's only one vendor system out there that consistently performed better than this system. And it compares well with all the other current vendor systems in terms of user friendliness as well as training on them. So the overall recommendations that came from this are really, all our recommendations are now data-driven and typically more reliable, which helps TSA make the case for developing a user interface that all these system vendors would have to abide by. The level of reliability of our recommendations to them could be quantified based on the experimental structure. And we validated quantitative findings against qualitative findings to help provide valuable insight for them. So while we did have performance and preference trade-offs noted and we couldn't interpret all the data that was available to us, it definitely strengthened our recommendations to TSA and their rationale that they could walk to vendors to and say, we need this information from you guys, we need you to use this interface for these reasons. And so this is a general process that's implementable, and it can provide all different types of testing platforms and protocols we can adapt this to. So the development of the common GUI interface was only one example of this process with human factors applied at TSA, but there are many other examples that they're currently trying to increase the use of human factors research and experimental design in their lifecycle development process. So specifically for the common GUI, we developed a specific prototype for initial implementation and the required tools for all systems regardless of the designs that we identified. And we also showed them which broad metrics can serve TSA over time. So using a standard measure like the system usability scale can help them establish standards for just development and procurement overall for all their systems, both for current systems as well as new systems in the future. General training considerations were also identified. So the development of a structured training, what elements of that training would be necessary for TSOs, and how to support the knowledge if required of these TSOs from one system to another and not put the burden on the user. As well, we identified ways to ensure that you have adaptability of systems to future projects. And so that again is our final interface, and that is the development of the common GUI following human factors process recommendations at the Transportation Security Administration.
Thanks so much, Chaz and Simon. That was a really interesting talk, and I personally look forward to the day when we can return to flying safely and send our bags to.
So do we.
So we'll take time for one quick question. If anybody has anything to type in, transition to our third speaker. So I'm not sure if you guys can see the chat window, but the question is, how different was the version 2 GUI from the one you guys did, the C GUI?
And so the vendor two one?
Yeah, sorry, vendor two.
Okay. Yeah, I'm trying to remember because we've obviously scrubbed the names. If I remember correctly, that one actually was relatively similar to the one that we developed. And ironically, it was the interface that most people liked when we did our review process. But at the same time, there were certain features and elements that the users felt were missing heavily, and they also needed to improve on with training regarding the system, that it wasn't as easily trainable.
Another mitigating factor I would throw in there is that vendor 2 actually had been in the field the longest, and the TSOs had been working with it for almost 6 months by the time we ran our iteration 3 test. Looked at those sus scores. I think that was a major factor in why they got such high scores, was the TSOs had 6 months to refine their workflows, their methodology, their SOP, and they were very comfortable with it. Whereas the other vendors, you know, like vendors 3 and 4, they've been in the field for like a month.
Yeah, and part of the problem with the low scores on them is that those systems regularly broke down, and the TSOs couldn't use them often. So they kind of associated with the fact that the system kept having bugs and breaking down with the system was unusable, whether or not, so they were mostly judging it on their ability to use the system as opposed to the system itself, I think.
Great. Well, thanks again, guys. And now we will transition to our third and final speaker for today, Dan Porter. So a quick introduction. Dan is a research staff member at the Institute for Defense Analyses. Before joining IDA, he earned his PhD in cognitive neurosciences from the University of Michigan. At IDA, Dan supports the Joint Strike Fighter operational testing, as well as the Air Force's Pilot Training Next program. In addition to that, he is the lead author for a framework for testing AI-enabled and autonomous systems, which he will be sharing with us. Thanks, Dan.
All right, thanks for that introduction, Rebecca. And to fill out everyone's bingo cards, can you hear me?
Yes, we can.
Okay, wonderful. Bingo. All right, so as Rebecca mentioned, I've been working with others on a framework for testing autonomous systems for about the last 2 years. It is a very long document, and it's only part 1 of 2. And I'm presenting a very tiny piece of that today. But we are almost through our internal review process, and it should be available soon. So if anyone wants that, you can go ahead and get in touch with me after this talk. But obviously, with a 120-page document, we've been doing a lot of thinking about how do we get enough evidence that systems that can make decisions for themselves are going to behave in an acceptable manner. Now, there is way too much that we have to test with these systems. So there's no way we can do any kind of exhaustive testing, especially not with live testing. So we're going to be relying a lot on inference and on simulation. But that also means we have to VVNA those simulations. And today, let's talk about why, especially for fully autonomous systems that are in the real world, especially if they're trained with machine learning, this kind of VVNA is going to be difficult. But what's the kind of root of all of this difficulty? It's really just because machine learning makes no distinction between correlation and causation. It can learn something that's associated with what you want, but not the thing you actually want. And the machine learning mechanisms we have, at this time at least, are the same that we have in pigeons and even in invertebrate sea slugs. So when people talk about learning in machine learning, it's not what people think about when they think about human learning. And personally, whenever I hear someone say, I've trained an AI to blank, I kind of just mentally replace the word AI with pigeon to decide how skeptical I'm going to be of that. And frankly, that might be a little unfair to the pigeon sometimes. Now, the pigeon and the AI are both going to learn something when you train them. But that might be something kind of stupid that only works in the test or training cases, and it's not going to work in real life. And if we can't be confident in what causes the system to make its decisions, both trying to infer or generalize so that we don't have to test exhaustively and VVNAing our sims so that we don't have to test everything live becomes pretty hard. And so let's talk about that first part of inference or generalization. Now, imagine you've got an autonomous car, and you want to know, is it going to be safe to drive? Is it going to stay on the road? And so maybe in that first curve there with the 100 out of 100, you've driven it a bunch of times and you have never, ever seen it drive off the road. Now, we're coming up to another situation, a new curve in the road, and the car has never encountered that before. And we want to know, is it going to be safe there, or is it going to drive off a cliff? Now, if we take that 100% success rate we've observed earlier, and we say that applies to this new situation, we're asserting that the similarities between these situations matter to the system, and the differences do not. We're asserting that we understand the causality of its decision-making. But when a system's a black box, that's not really an assertion you can make validly. I might understand really well how its sensors work, how LiDAR functions. I might understand how the mechanics of its actuators work. But that doesn't tell me anything about how the system makes decisions, about how information in the environment is going to change its behavior. If you're going to predict decisions, you need to know at minimum what its goal was, what it perceived the situation to be, and how those things interact for the system to select its next action. These are the fundamental atoms of decision-making. These are what cause behaviors. So if you're going to make valid generalizations, we need to have at least a useful model, and I mean a useful model the way George Box means it, of how the system's decisions work. Now, in testing, we are used to doing things like objectively recording behaviors, our outcomes of interest. And we're also used to instrumenting sensors and actuators to diagnose if something goes wrong, or just make sure they're not responsible for some bad thing that happened. And the paradigm shift we need in AI-enabled systems is we also have to instrument the system decision processes. And we have to do that across the system's life cycle. So at the minimum level of granularity, this should tell us what was the system's goal, what was it trying to do, what did it perceive the situation to be, and what was the action it tried to execute. And some people, including some people I think are still in the audience, call this cognitive instrumentation. So these three boxes are kind of the fundamentals of having a model of system decision making. And so let's go back to our autonomous car. Let's imagine it has both passive video sensors and LiDAR. Now, you might imagine a world where with this passive video system, maybe the way it perceives the edge of the road is through color contrasts. So you get these really nice contrasts between the black asphalt and the yellow line, and also between, the curb and the asphalt. If that's how you believe the car perceives the edge of the road, the obvious question is, well, how much contrast does it need to be safe? And that's something we can test, right? Maybe we pick some test points, we vary the color contrast, and we observe its behavior. And then we're going to be good statisticians and we'll make inferences between those points. Now, that's what we do in our standard systems, and that's probably fine there. But with systems that learn things on their own, again, real world information dimensions are confounded. And so maybe your training environment always had some kind of rise in elevation, like there's a sidewalk or a berm or a curb. And that's everywhere that we train the system. Now, machine learning could have just as easily picked that up as color contrast. And so if we go back to our first example, maybe that first curve where we've done all of our testing had both of those pieces of information. We both had color contrast and a rise in elevation. But this second curve, maybe it only has the color contrast. Depending on which of those perceptual models you think is true, does it use the color contrast or not, you're going to make very different predictions about its behavior. And so if I see in this new situation, it goes and drives off the cliff, well, in addition to being really bad, that's evidence against my model that the edge of the road is defined by color contrast. But if I knew that in advance, I maybe could have avoided that situation in the first place. We could have avoided that kind of unintended behavior. And so we have to get a model of how we think the system makes its decisions. But that's not going to be enough. We can't just obtain that model. We also have to put in work to show that model is good enough for our purposes. So we have to obtain, verify, validate, and accredit those models of system decision making, or what we're calling OVA. We need to do this so that we're confident we're varying the right information in tests, and that we're making inferences between and beyond our test points that are valid. All right, so I'm just going to pause real quickly and let everyone know, if you have questions, feel free to type them throughout. I have the chat open, and I'll do my best to answer as we go. But anyway, so let's dive into this OVA process. But first, I want to try to head off some confusion when we're talking about VV&Aing, because this can apply to more than one thing in testing autonomous or AI-enabled systems. So when I talk about OVA, we're talking about trying to understand what causally drives the different types of systems, the different types of decisions a system can make. So, sorry, I had to admit someone to the talk. All right. So when we talk about OVA, that's what we're talking about, that box there. But we also need to VV&A the simulation environment where we're going to test the system's behavior. Now, the real confusion and the real challenge, though, is that we can't fully VV&A either of these things without the other. For example, to verify the behavioral simulation, I need to understand what the system needs to perceive and what it cares about in the environment before I can do that. So imagine you have a helicopter and you want to add some AI-enabled threat detection system on that. Well, a perfectly reasonable person might say, all right, well, I care about tanks. I want to represent those in the simulation. But I'm not going to have a perfect, super high fidelity tank. I'm going to have an Abrams. I'll have a T-72. And I will verify the LiDAR or radar returns on those. That'll be accurate, but we're not going to have the turret rotate. The barrel's not going to elevate or depress. That's more detail than we need. That intuitively, that might seem perfectly reasonable. But if you have a black box machine learning system, that angle of the barrel may be important to it. And if it's not represented in our behavioral simulation, the behavior we observe there is not going to be valid. So to verify that behavioral simulation, again, we have to understand how the system perceives the world first. But we're also going to need this behavioral simulation to help test our decision model. So if I think that the system perceives the edge of the road through color contrast, but I see it drive off when it's present, well, that might invalidate that model. And so the different things that need to be VV&A'd feed back into each other. And that feedback loop is going to get us closer to the title of this talk about why the loop is hard for fully autonomous systems. Now, two really big things. First, OVA is going to be iterative. We are going to fail, and we need to be ready for that. So after we obtain the model, we're going to need to test its behavior and see whether that model is good enough. And when we fail, we need to go back. And secondly, all of this has to happen before what we normally do in DT and in OT to do performance testing. This is a necessary but not sufficient condition, at least as our team argues, before you can do that. Now, I'm just going to flash up this here very quickly, just to let you guys know, there's a lot more detail I'm kind of glossing over here on how to execute these boxes that we go into in a little bit more depth in our paper. But let's talk now about OVA and the obtaining that model first. And why is this going to be hard? Well, first, how you obtain a model depends on how the system is designed. So up here I have two dimensions. They are not orthogonal. They're a little bit correlated in real life. But between whether your system uses sub-symbolic or symbolic processing, and I'll explain that in a moment, or whether it's monolithic versus modular in its architecture. So symbolic versus sub-symbolic processing, for most of you who haven't encountered those words before, this just basically means, is the information representation and the processing the system does intelligible to a person? So in a symbolic system, a cat might be represented either by the word CAT or by a picture of a cat. It's something that is innately intuitive to a person. Whereas in a subsymbolic system, the concept of a cat might be represented by activating node 581 and 13 and 37 all at the same time. That's not really meaningful to a person. And in monolithic versus modular, this has to do with how inputs relate to each other. So in a monolithic system, all of your inputs occur in parallel, and every possible output the system could produce is also in parallel at the end. Whereas a modular system, you might have a box that takes inputs and produces certain outputs, and those outputs act as inputs to the next box. So things like deep neural nets tend to be more subsymbolic and more monolithic, whereas our traditional software tends to be more modular and more symbolic. Now, I'm very intentionally using more here because these are dimensions. These aren't binary. You can have hybrid architectures where maybe I have a small neural net that takes symbolic input and transforms it somehow into different symbolic output. And that's going to then feed into another neural net. So the reason this matters for obtaining is that depending on which of these poles you're at, you either need more data-driven methods to obtain the model, or you might be able to just look at the designer's choices to figure out what the decision model might be. And so let's dive in a little bit more detail into how to obtain with data-driven methods. So if anyone has seen Dave Gunning talk or anyone else from DARPA's explainable AI program, you may have heard about model induction. And that's going to be one of the more promising methods we have to obtain a model for a black box system. Now, even in a black box, we know that certain inputs are going to reliably produce certain outputs. And in things like computer vision, you can build things that, like salience maps. So up here, I have an example where I can compute for any given image how influential was each pixel in what the machine learning algorithm thought it was saw. Excuse me. Now, this is basic. We've been doing this for years, but what model induction is doing is they're doing things like having people draw bounding boxes on different parts of the image and sub-labeling those. And if we do this a lot and feed it through some different methods, we can start to turn that black box a little more transparent and find that the way DOME is represented is through this, this layer in the neural network or this set of nodes. And it allows us to get a little bit more transparency into that system's intermediate processing. Now, I'm glossing over a lot of very important technical distinction in the model induction work. But one thing pretty much all of the methods assume is we have operationally valid inputs we can feed the system. And if you have a passive perceptual system, you know, like Project Maven or anything that does computer vision, that's probably met. We have a lot of pre-recorded mission data we can just feed into the system. And this is also going to be true in purely cyber systems. Because, you know, all right, a video game bot, its actual operational environment is by definition, you know, a simulation or something that's going to do cyber operations. That's also true. But in a fully autonomous system, something that can perceive its environment, choose its own goals, and move around, well, that kind of system can change the information it can acquire. And so if I have a drone that's trying to recognize different objects, if it can't see it from one angle, it might change where it flies to try to identify it better. And that's not something it can do in pre-recorded data. So this is where we hit our catch-22. How are we going to obtain the data we're going to use to obtain our model? Because we need this perceptual model, at least, to verify our simulation. And we can't really test live because we're going to need to get a safety release for that. And the current consensus is we're going to use our simulation to get that safety release. And so with these fully autonomous systems that are trained with black box methods, really the only way we see forward right now is to move slowly. Fortunately, if anyone has saw Jim Simpson's talk the other week, something that's really going to help us out here is sequential experimentation, where instead of planning these tests out 5 years in advance and we know everything that we're going to test, we're going to have to experiment. We're going to have to see and find things and adapt over time. And we're going to want to, one of the things we're going to want to adapt to is how informative are these test points about my system's decision model. So I'm going to fly through this really quickly to try to stay on time. But for example, if I have a system that's supposed to recognize buses and I give it one test and it does really well, hey, yeah, that is a bus. But then I give it a construction vehicle and it says that is also a bus. You can play this game with your 4-year-old if you want to. So I have to ask myself, well, why is it identifying the thing as a bus? Does it just think everything that's yellow is a bus? So maybe I throw a white bus at it and it says, oh, that's not a bus. But if we're doing sequential experimentation, the scientists in the audience probably know this was a dumb thing to test because I've manipulated 2 things at once. I've both made it a flat-fronted bus and I've made it white. And so we're going to want to think carefully and develop methods that help us test these hypotheses about the decision model more efficiently. Now, when we get these more subsymbolic, more monolithic systems that are fully autonomous, we're going to have trouble getting the data. It's just going to be a problem, and we need to be ready for that. But fortunately, that's not the only way we can design AI-enabled systems. And if we go towards a more hybrid architecture, for example, like I mentioned, a bunch of neural networks that feed into each other, we can use other methods. Because in these different black boxes, I know what content they take. I know they take certain kinds of information. So for example, I go from my video feed of pixels, and my first box just detects edges. And then it's going to feed the Cartesian coordinates for all those edges into another box that's going to construct shapes out of them. And then another box takes all those shapes and figures out which ones belong to each other. And this is just a toy example. I'm not recommending we build a system like this. But if I have a system like this, I can isolate the different boxes and feed them synthetic input. I know what it takes, and so I can synthesize that and feed it in. And so this is the standard kind of compositional verification a lot of people do on their software. The difference in these AI-enabled systems, though, is these might not be deterministic systems. They may be, but they might not be. And so we want to change this obtain and initially verify step into something that's a little more cascading, where maybe I start at an earlier box, and then I see what the downstream result is. I don't just verify each box individually. And we can do this both from the top down and the bottom up through our architecture. Now, one thing we are working on the test science team at IDA is this idea of Bayesian network modeling of, all right, I know that each box is not perfect. I'm going to estimate its performance, and that's not going to be perfect, but my estimate is also going to be imperfect. And because these are garbage in, garbage out, errors can compound through the network. And so we need methods for propagating both that estimate uncertainty and the actual error rate of the module throughout the network to get a better understanding of how it's functioning. So if we can do this, we don't necessarily need to do live testing. We can just do this kind of synthetic injection with compositional verification. So just to wrap up really quickly, if we are going to test these systems, we are going to have to rely on inference. We need to know how environmental information changes behavior in order to make those inferences valid. So we therefore need to obtain, verify, validate, and accredit those models. But when we get into fully autonomous systems that are black boxes, this gets really hard. But fortunately, we can mitigate those challenges both with sequential experimentation and if we have more hybrid systems, this problem gets a little bit easier. So with that, I'm going to open it up for questions. Thank you all. And if anyone wants a copy of our paper when it's hopefully released very soon, just get in touch with me at that email. Thank you, guys.
Thanks, Dan. And as he mentioned, we'll stay on for any questions that you guys might have. And while we're waiting for any questions, I'll just make a quick announcement that our last and final webinar will be held May the 29th. We're going to take a pause next week in case anybody wants to take a 4-day weekend for Memorial Day. But I encourage you to check out our DataWorks website. We have a little promo video up there as a teaser, and we hope you can all join us for our final session. Dan, it looks like you have one question then.
Yep, see it from Len. So Len, do you think, do I think that standard hypothesis testing, like making predictions and then seeing whether they're true, will work for decision testing? Is that what you're asking? Yeah. Yeah. Yes and no. I think it's going to depend on the system's complexity. One of the things that system complexity is definitely going to make the standard tools we use for hypothesis testing inadequate. And that's one of the things that we're going to need method development for. So I know Rebecca is, for example, working on some sequential test design stuff, you know, and that's one of the things we're thinking about. So the cop-out answer is maybe.
If there are no other questions, I do want to thank our 3 speakers again for the excellent talks and taking time to share your work with the rest of the community. So with that, I think we'll call it an end of the day. I hope everybody can get outside and enjoy the weather that we have today, and that you have a great weekend.